Hi everyone, I'm Eren Gürbüz. I'm a second year CS student at Bilkent University. Today we are going to conduct an experiment on Airtable, and the name of my experiment is effect of launch angle on Airtable in projectile motion. So main aim of my experiment is to investigate the launch angle to the horizontal range and maximum height of the projectile motion. So let's introduce our equipment. First of all, we will use Airtable, and we will put a wooden block under the Airtable to provide an incline to Airtable. We will use puck of the object of our projectile motion. We will use the white paper and the carbon paper. We will use the spark timer in order to put dots on our paper. So we will need to use also two pedals right there. One makes the Airtable frictionless and other makes the dots on the paper. We will use spring to initialize our projectile motion. To determine the launch angle, we will measure the both vertical and horizontal length of the spring compression, and also in each projectile motion we will try to make spring compression equal in order to avoid the effect of the launch speed to our projectile. First, we have made the launch angle 45 degrees. As you can see, this is a perfect projectile motion. This time we have made the angle 30 degrees. The white paper, we will measure the maximum height and horizontal range for each projectile motion and compare the effects of launching. From graph 2, we can see that starting from 15 degrees, the horizontal range increases as the launch angle approaches 45 degrees. After reaching 45 degrees, the range begins to decrease. This behavior is explained by the general formula for range, which contains the term sin 2 theta. Since sin 2 theta reaches its maximum value of 1 when theta is 45 degrees, the horizontal range also attains its maximum value at launch angle of 45 degrees. From graph 4, we observe that the maximum height increases steadily as the launch angle increases. This trend is consistent with the theoretical formula for maximum height, which contains the square of sin theta term. The maximum height becomes larger at higher launch angles. Since square of sin theta increases continuously from 0 degrees to 90 degrees, the maximum height also increases over this range. Therefore, among the tested angles, the projectile reaches its highest point at 75 degrees, where square of the sin theta is the largest. From the slope of the graph 1, we can find that initial launch speed of the projectile motion is equal to 0.83 meters per second. However, we have found from the table 2 that measured average launch speed for our projectile motion is 0.82 meters per second. This will cause a percentage error as 1.22%. Similarly, from the slope of the graph 3, we can find the initial velocity of our projectile motion as 0.86 meters per second. Yet, we have found from the table 3 that measured average launch speed for our projectile motion is 0.82 meters per second. Again, This will cause a percentage error as 4.9%. Even though we have some uncertainties, we have measured the initial velocity of projectile motion with different methods and we have not seen a high percentage error. This proves the accuracy of our experiment. Even though we have not seen a high percentage error, we have still a possible sources of error, which is inconsistent launch velocity, friction on air table, and measurement uncertainties. Also, human error may cause some errors during the release of the puck from the spring. Air resistance and friction between the puck and paper cause loss of energy. This will lead to deviations from the expected horizontal range and maximum height. The last reason for the possible source of error is measurement uncertainties. This might be caused from the ruler or true maximum height for the projectile might have occurred between the two dots on the white paper. This could lead to small deviations from the original values.